the next speaker in this session, Alastair Young from Imperial College, speaking on Bootstrap and parametric inference, successes and challenges.
Thank you very much. Okay, here's an overview of what I want to do, and also in the process of this want to make an admission that perhaps much of what I'm going to say isn't as directly relevant to the main themes of the workshop as the talks we've heard so far. I want to start really by reviewing some of the key aspects of frequentist parametric inference as it developed over the last 25 years or so. And of course, I don't want to just look backwards. What I'd like to try and do is to look to the present, and in particular, the kinds of more complex parametric problems that perhaps are relevant to the areas that this whole program is going to address, by really asking, on balance, what should be the inferential approach of choice when presented with parametric problems. Now, given the title of my talk, it will come as no great surprise that what I'm going to argue, I hope with some justification, is that in fact very simple simulation approaches, bootstrap approaches, appropriately implemented, perhaps provide that inferential approach of choice. Now, most of what I'm going to be talking about, is going to be, in fact, considering cases where we've got rather low-dimensional parameters. In fact, the bulk of what I'm going to say is going to concern the case p is equal to 1. Hence my doubt about whether things here are entirely irrelevant. And indeed, I'm going to give an example later where p, the dimension of the parameter, is 1, and the data sample size n is equal to 2. Okay? So what I'm going to do is, I hope, trade relevance by being provocative and perhaps saying some things that certainly, if the likelihood inference gang were here in the audience, might make me quite unpopular with them. Because what I'm going to argue is, in fact, that simple bootstrap simulation procedures are crucially, provided we handle the nuisance parameters in the parametric models appropriately, they do provide a very satisfactory, very simple approach to parametric inference, and I think this is the crucial point of my talk, whilst retaining finer inferential components of statistical theory. Of course, one of the great questions that will have immediately arisen to you is whether, of course, those finer inferential components are actually relevant nowadays. And so, as I go along, and certainly at the end, what I want to do is to flag various issues and theoretical questions that it seems to me would be worthy of development, in particular during this workshop. Now, I should immediately acknowledge that any point of rigor or substance that I'm going to make in this talk is contained in joint work in various papers with Tom DeCiccio, Stephen Lee, and Russell Zaretsky. So the results, the key theoretical results, are in joint work with those co-authors. Okay, let's do as I promised then and think about what are the key features of frequentist approaches to parametric inference as they have been developed over, say, the last 25 years or so. It seems to me that the key driving force behind these developments has been the idea of trying to construct inference procedures which yield accurate inference, say, yield confidence sets with actual repeated sampling coverage close to the nominal desired coverage, that yields that kind of accurate inference with small sample sizes. Okay? Modern statistical theory has generally been driven by the desire to be able to do things accurately with small sample sizes. At the same time, though, these procedures, I think it's fair to say, have been explicitly developed or constructed to respect what I was referring to before as finer points of parametric theory. They've been constructed to respect key principles of statistical inference, in particular conditionality principles. And I've already admitted this, the focus has generally been on the case where the interest parameter in our parametric model is of low dimension p, typically p is equal to 1, but I think it would be fair to say that the procedures are very often calibrated or validated, justified in terms of their ability to accommodate nuisance parameters of high dimension. Think of a very simple problem, say the inference problem of inference about the common log odds ratio in a stack of 2x2 contingency tables, the kind of problem on which there has been very much debate over many years. You can't get away with suggesting some kind of sophisticated analytic parametric inference procedure unless the method is going to accommodate inference in that kind of setup where you've got a high dimensional nuisance parameter. I suppose that idea relates to what you might think of as a sort of 20th century view of how science progresses, which is perhaps encapsulated in this quote from David Cox. This idea of looking at one-dimensional interest parameters predominantly really stems from the way in which science proceeds by breaking the research question of interest down into a series of simple components, each of them corresponding to some very strongly focused research question, which can be phrased in terms of inference for some scalar or at least low-dimensional quantity of interest. The other key characteristic, I suppose, of developments in parametric frequentist theory over the last few decades has been an interest in developing procedures that work with fairly general classes of statistical model, these classes of model where this idea of inferential subtlety, finer components of theory, as I called them before, are important. And of course, primary amongst those is the idea of an exponential family of distributions as the parametric assumption that we make. And then also, of course, the other main setup where theory has been developed, that of transformation models. Transformation models simply where you've got some group of transformations on the sample space for your random variable, inducing a parametric family of distributions with different values of the parameter, but remaining within the same class. Or more generally, I suppose, models which admit ancillary statistics. And I'll come back to make a formal definition of what I will take an ancillary statistic to be a bit later on. Okay? So that's the key characteristics of what I see parametric theory as being at this time. Now, I'd like to take at this point the time to define a particular inferential problem, okay, and to make some restrictions in what I'm going to look at purely for simplicity's sake before we come back and look at the main approaches which we can take, which may encapsulate some of these characteristics that I've described, okay? So the inferential problem that we're going to look at is one where we've got our data, y, consists of a random sample of size n, y1 up to yn, where the yi's need not be scalars. They could be random vectors, of course. But we assume that that random sample comes from some underlying parametric distribution, capital F, indexed by some possibly high-dimensional parameter vector eta. D I'll use to denote the dimension of the full parameter vector. But we are actually interested in the parameter of interest is some parameter theta, some appropriate function g of eta of dimension p, where p will typically be low. In most of my discussion, p equal to 1, but perhaps p of some other low dimension. Okay? Now, to try and pin things down a little bit, let's suppose without loss that in fact the thing's parameterized so that the full parameter vector eta is decomposed as 2 bits, right? Theta, which will be the p-dimensional parameter of interest, and some q-dimensional nuisance parameter lambda. Okay, so crucial to much of what I'm going to say is the appropriate handling of that nuisance parameter lambda. And just to make things precise, let me suppose that the inference problem that we've set ourselves is to test on the basis of our data y consistency with some null hypothesis that says about the interest parameter that it takes some specified value theta naught, say, or using the familiar duality, suppose what we want to do is to construct some confidence set for that parameter theta of some nominal repeated sampling coverage, okay? In the case where p is equal to 1, so we've got a one-dimensional interest parameter, we want to allow ourselves to do one-sided inference. So for example, we want to test our null hypothesis, the point null hypothesis, that theta is equal to theta naught against a one-sided alternative that says either theta is less than theta naught or that theta is bigger than theta naught, or we want to construct a one-sided confidence limit for that parameter theta, okay? Okay, how, this is the patronizing bit of the talk, right? But you can take it as being an attempt simply to set up some further notation. How might we go about doing this? The focus of my talk is going to be the performance of these simple simulation, parametric simulation methods, bootstrap procedures, when we are working with likelihood-based inference methods, okay? And to that end, we'll denote by little l of eta the log likelihood for the full parameter vector constructed from the data sample y. And I'll denote by eta hat, so consisting of theta hat and lambda hat, the overall, the global maximum likelihood estimator of the full parameter constructed from y. And then for a fixed given value of the interest parameter theta, we'll denote by a lambda hat subscript theta, the constrained maximum likelihood estimator of the nuisance component of the parameter vector, okay? Now, I would like to concentrate, really largely for simplicity of presentation rather than for any other particular reason, on inference based on the first hand, the familiar likelihood ratio statistic, which I'll denote by W of theta, which is just twice the difference between, of course, the log likelihood at the global MLE and the log likelihood when you shove the interest parameter to be theta. Okay, W of theta, you shove the interest parameter theta and replace the nuisance parameter by its constrained maximum likelihood estimator. So that's the familiar, the most simple. I'm not sure that I learned about likelihood ratio statistics when I was 17, but I wasn't probably much older than that when I first met likelihood ratio statistics. In the case that I'm going to be considering predominantly, where the interest parameter is of dimension p is equal to 1, inference would be based on the sine square root of that likelihood ratio statistic that I'll denote by r of theta. So we just take the square root of the likelihood ratio statistic and multiply it by a thing that tells us the sign of the difference between theta hat and whatever the theta that we're interested in, okay? That being the case, though, I would like to immediately acknowledge that lots of other possibilities immediately spring to mind from that early education in parametric statistics that we had, things like walled statistics, score statistics, and variants of these procedures based on modified likelihoods and all that kind of stuff. And though I'm not going to really say too much about that, I'd like to acknowledge at this stage that, broadly speaking, most of what I'm going to conclude about, in particular, performance of these simulation procedures will hold. Most of what I'm going to say will hold for these other kinds of statistic as well, okay? Though it seems, and another reason for focusing on it, that inference based on the likelihood ratio statistic or its sine square root tends to be, particularly great, right, in the kinds of situation that we might be interested in looking at, and certainly would provide the basis for a recommendation of how you would go about something more complicated, right? Okay, now we can, the attractiveness of those statistics, the likelihood ratio statistic and its sine square root, of course, is that with some generality we have a ready placed first order asymptotic theory that we can appeal to do the inference. In particular, in a first order theory, we know that the sampling distribution of the likelihood ratio statistic is chi-squared on p degrees of freedom. Remember, p is the dimension of my interest parameter. It's chi-squared. The distribution of the likelihood ratio statistic is chi-squared to an error that's of order n to the minus 1 in the sample size. N was the size of my sample. For the sine square root version, things ain't necessarily in terms of order of magnitude of the error so great. The sine square root likelihood ratio statistic, R, is distributed as standard normal, but now to an error that's of order n to the minus a half in the size of the data sample. Okay? But there's a ready-made, if crude, inference procedure that we can use, which is simply to refer the values of the likelihood ratio statistic or the sine square root, depending on which we're interested in, to the asymptotic distributions for, in the two cases, chi-squared or standard normal. Okay? But much, of course, of parametric statistical theory over these last decades has been designed to try and improve upon those levels of approximation. Okay? Now, before we sketch the main methods, and of course you can see what's coming, by which we can effect that kind of improvement, I'd like to say a little bit of about each of the two main contexts that I highlighted earlier as being very central to the development of statistical theory. The first of those is the multi-parameter exponential family context. A full exponential family model. Suppose that the log likelihood for the full parameter eta in our model can be written this way. Remember, theta is the interest parameter. I've written this in such a way that it needn't yet be scalar. And lambda is the nuisance parameter. So suppose the log likelihood is of that full exponential family form, so that theta, the interest parameter, is the natural parameter in a multi-parameter exponential family model. Then, okay, what do I mean by inferential subtlety in this context? You will remember from that basic statistical theory course that you took a long time ago, perhaps, that in such a model, the conditional distribution of the statistic S1, the natural statistic S1 that's associated with the interest parameter, conditional upon the value of the statistic S2 that is associated with the nuisance parameter, that conditional distribution depends only on the interest parameter theta, in the sense that conditioning on the observed data value of S2 is a means by which we can eliminate the nuisance parameter lambda from our inference. And so the procedure and appropriate inference in this setting for performing inference on that theta of interest is an inference which is based on that conditional distribution of S1 given S2. In principle, if, for example, once we fixed, say, the null hypothesis value of that parameter theta, that conditional distribution is something that's known to us, right? Because it doesn't depend upon the nuisance parameter lambda. That's been eliminated by the conditioning. And I like to think of that conditional distribution as furnishing us with some kind of ideal bootstrap solution to inference on theta in such a model. Ideal in the sense that there's no nuisance parameter or anything messing up our life anymore, and the relevant sampling distribution to be using for the inference is something that is in principle known, right? Now, the reason, apart from the obvious reason, oh great, by doing the conditioning we've eliminated the nuisance parameter, that this kind of inference procedure might be attractive, is that the conditional inference that we effect by that procedure actually has an unconditional, say repeated sampling, optimality property of actually being uniformly most powerful, unbiased, etc., etc. All those kind of things that we learned about a long time ago. So that's by means of saying that in this full multi-parameter exponential family setting, it's clear what is the inference that we should really be aiming for. Okay? The problem is that that inference, that exact inference, that ideal bootstrap inference, as I termed it, is in practice either awkward at best, or in many circumstances quite impossible to work with. Okay? The relevant conditional distribution, so the conditional distribution of S1 given S2. Typically, for its construction, requires very awkward analytic calculations, numerical integrations, and stuff like that. I'll give an example later of a case where, in fact, that conditional distribution is simply not tractable. So that means that the ideal bootstrap procedure is very often practically infeasible, so we've got to do something else about it. Okay? Okay, so that's one of the two main setups where statistical theory has been developed. The other, I termed transformation model setting, is the case where there are ancillary statistics kicking around. And what's going on here is what I term the Fisherian proposition, Fisher himself, that says that inference about our parameter theta of interest should be based not on the original parametric model that we set down, so the model that I called Fy, depending on the parameter vector eta, but instead on some derived model that we get by conditioning on an ancillary statistic when such a thing happens to exist. Now here is formally what we will take that to mean. I think this is now, by now, after much debate, a fairly universally accepted definition of ancillarity. We will say that A is ancillary if the minimal sufficient statistic for the full parameter vector eta in the model can be written or decomposed as consisting of 2 bits. The global maximum likelihood estimator of the parameter eta and this statistic A, where A is at least approximately, and I won't bother to define that that idea of approximately too closely, A is approximately distribution constant. Okay? Then if that's going on, that's when we say A is ancillary, and formally the conditionality principle of inference would suggest, or perhaps depending on your point of view, would more strongly dictate that to be relevant to the data that we've actually got before us, the data that we're doing the inference on, the inference on theta should be made conditional upon the observed data value of that statistic A, that ancillary value A. Okay? So that's the two setups. So in both cases, there's some inferential subtlety involving the idea of a need to condition, right, that should be encapsulated within our inferential approach. Well, what about these refinements to this basic first-order parametric theory based on the asymptotic, standard normal, and chi-squared distributions? What kind of refinements can we make? As we said, the driving force behind them is generally to obtain higher order accuracy, to reduce the level of the error in the inference, whilst encapsulating the needs of these, in particular within the two contexts that I've described, the need for conditioning. Okay? But really, there are two approaches to that to achieving that higher order accuracy. There are analytic approaches based on what I think are now conventionally known as small sample asymptotic methods, by which we mean things like Laplace approximation, saddle point methods, and related kinds of approach. And that's been the general focus of parametric theory, I guess, over the last 20 or 25 years. But, of course, what I'm presenting here, or suggesting here, is that, in fact, very simple simulation or bootstrap methods stand the test when put up against these parametric procedures as being the kind of inferential approach of choice in terms of obtaining higher order accuracy and automatically retaining, right, these the kind of inferential subtleties that the analytic procedures are designed to encapsulate. Okay? Okay, taking the analytic methods first, what are the highlights? This is a little bit personalistic to say what are the highlights of an enormous industry in parametric statistical theory. To me, the two main highlights, I guess, are on the first hand, the simple idea of Bartlett correction of the likelihood ratio statistic that I called W theta. And on the second highlight has been the development of analytically modified forms of the signed square root of that likelihood ratio statistic that are specifically constructed to offer conditional validity in terms both of the conditioning that's desirable in the exponential family context and the conditioning on ancillary statistics in the ancillary statistic context, analytically modified forms of the signed root statistic that give us conditional validity to some high or higher asymptotic order in the sample size. And the most famous, I suppose, of these analytically modified forms is Barndorf-Nielsen's R-star statistic. Okay? So taking these two ideas in turn, the idea of Bartlett correction, I guess, will be familiar to most of you. The idea here is simply that if we look at the expectation under repeated sampling of the likelihood ratio statistic, then we can get an asymptotic expansion in powers of n for it, where it's p, which is the expectation, remember, of the asymptotic chi-squared p, times a factor that's of the form 1 plus something that unfortunately depends on the full parameter in the model divided by n. But the structure of that expansion for the expectation suggests that we can modify the statistic, the likelihood ratio statistic, by just effecting some kind of scale adjustment. The kind of scale adjustment is that we derive by just looking at the leading terms, the 1 plus thingy over n term in the expansion for the expectation. And it turns out, in fact, that in the handling of that term, if we do, and you'll notice again that I could call this a bootstrap calculation, if in the expectation term, the term in the expectation b of eta, we simply replace the nuisance component of the parameter eta, so we replace the lambda by its constrained maximum likelihood estimator, and then do a scale adjustment of the statistics by dividing through by that factor, then we get a modified form of the likelihood ratio statistic, W dashed, say, which turns out to be chi-squared on p degrees of freedom, but now to an error that is of order n to the minus 2 in the sample size rather than the n to the minus 1 that we had before. Okay? So that's a kind of attractive thing. So what we could do is we could just modify our likelihood ratio statistic by this multiplicative factor here, which just requires us to plug in the constrained MLE of the nuisance parameter, and then effect our inference on theta, the interest parameter, again by referring to its asymptotic chi-squared distribution, and that tends to be seen to work out to work in practice very nicely. The other highlight, Barndorf-Nielsen's R star. Remember, the idea there is adjusting and working not with the signed square root likelihood ratio statistic R of theta itself, but some adjustment of it. The general structure of the R star statistic is shown here, which is defined in terms of R, and some adjustment factor that I've simply called U of theta. Now, the form of that adjustment, I will not make you feel ill at this stage in the afternoon by showing. Let it just be said that calculation, even in simple cases like the multi-parameter exponential family setting, of that adjustment factor that allows us to calculate the R star statistic, that adjustment factor typically necessitates two things. Well, firstly, and this is actually quite an important point, I mean, it looks like a sort of trivial observation, but I think is inferentially quite important. It actually requires us to specify what is the ancillary statistic that we consider it relevant to do the conditioning on in the ancillary statistic or transformation family context. And then, in both contexts, the ancillary statistic context and the exponential family setup, it turns out that calculation of that adjustment factor U of theta requires very awkward analytic calculations, which typically require, in fact, approximations to be made, which kind of dilute to some effect the effect of having done the adjustment and having worked with the statistic in the first place. Now, why is it worthwhile, though, if you can do it, calculating that adjustment? Well, the answer to that is that the sampling distribution of the adjusted statistics of Barndorf-Nielsen's R star statistic is now standard normal, so the same asymptotic distribution as we had before for the unadjusted statistic, but now to an error that is of order n to the minus 3/2 in the sample size. The error, remember, was n to the minus 1/2 before. So we get third order accuracy, and in fact you get third order accuracy conditional on the ancillary statistic. Okay, so you get it, if you like, if you do your inference by making standard normal approximation to the sampling distribution of R star, you get an inference that approximates the appropriate conditional inference to an error that is of order n to the minus 3/2 in the sample size, and that, again, is judged to be pretty good. Okay, that's what we're saying in the ancillary statistic setting, and also we get the same kind of respecting of the appropriate conditional inference in the other context, the multi-parameter exponential family context. You get the exact conditional inference on my ideal bootstrap solution being approximated to third order by the inference procedure that you get by just referring R star to its asymptotic standard normal sampling distribution. Okay, so that's why you might it might be worth doing R star. Okay. Now there's a lot of evidence, a lot that can be said about these and other analytic methods of parametric inference. I'd like to just make a few comments here and then move on, of course, to the main gist of what I wanted to say. Well, the first comment I've already said. Typically, in order to use these things, you have to be willing to specify what is the ancillary statistic that you want to do the conditioning upon. Very often, we've got awkward analytic calculations that may indeed have to be approximated to in their construction. Nevertheless, in recent work by Anthony Davison and co-workers, these analytic methods have been successfully packaged, at least within certain classes of model. There's an example there, nonlinear heteroscedastic regression models. All the time here, remember, we're still thinking of the fixed p, fixed dimension p, increasing sample size n kind of regime. Another thing which perhaps I'll come back to if time permits later, something that strikes me is that something that is relatively unexplored is, of course, the use, even within the sphere of these analytic methods, and in particular, the idea of Bartlett correction, of actually using this simulation, right, to replace the analytic calculations. Some time ago, I think about 1990, Peter Bickel, for example, suggested use of jackknife and related kinds of methods as an alternative to the analytic calculation of the Bartlett correction factor. And one possibility which we can think about is let's do simulation, right? Let's do a bootstrap simulation to replace the analytic calculations that I've said are typically very unpleasant or awkward. Another comment, perhaps somewhat in passing, is that most of what's been done in this area does refer to the case where the dimension p of the interest parameter is equal to 1. Versions of these R star type statistics are possible for vector interest parameters as well. But I guess the primary conclusion that one would draw from the literature on these things is that these kinds of things tend to be less effective with higher dimensional interest parameters than they are in the case where the interest parameter is one-dimensional, or than Bartlett correction type ideas. So no one in the right mind would want to work with versions of R star with vector interest parameters. Okay, so that's some comments on analytic methods. What's the alternative? What's my simple simulation alternative? What I've termed here the constrained bootstrap alternative to doing these analytic calculations. Well, the basic idea, of course, behind the bootstrap procedure, the bootstrap calculation, is that of estimating the sampling distribution of whatever our chosen statistic is by asking what is that sampling distribution under sampling from some fitted model that we construct from the given set of sample data. And key here is the idea of what I've termed a constrained bootstrap, because the procedure of choice comes about by appropriately handling of the nuisance parameter in that fitting stage that is the starting point for the simulation driven inference, okay? And the particular suggestion is that we should use as the basis of the Bootstrap calculation the parametric model that we've chosen to work with, f, but with the parameter in that model being set so that for any particular value of the interest parameter, we replace the nuisance parameter by its constrained maximum likelihood estimator. By contrast, a conventional sort of bootstrap calculation, a conventional parametric bootstrap calculation would use as the fitted model the model that you get by fitting the parameter to be its global maximum likelihood estimator. That's what we kind of first learned about the parametric bootstrap from. Okay, so the suggestion here specifically is that we have to handle the nuisance parameter by shoving it to be the constrained MLE of for a given value of the parameter of interest. Now, what are the properties of this kind of simple simulation bootstrap procedure? First of all, from a repeated sampling perspective, the story is basically that you get everything that you get from these analytic, sophisticated analytic methods by this kind of bootstrap procedure. Okay? In particular, if we're doing inference, say on a vector interest parameter theta based on the likelihood ratio statistic, it turns out that the bootstrap procedure that I've just described estimates the true sampling distribution of that statistic, again to error that is of order n to the minus 2 in the sample size. So you get the same order of error, right, from the bootstrap calculation as you did from the analytically more awkward Bartlett correction kind of procedure. In the case of a one-dimensional parameter theta of interest, where we're doing our inference based on the sine square root of the likelihood ratio statistic, it turns out that we estimate, using this constrained bootstrap procedure, the true sampling distribution of that statistic, again to third order, to an order of error that is of order n to the minus 3/2 in the sample size. And that's the same, right, as the order of error that we got by standard normal approximation to the sampling distribution of the adjusted signed root statistic. In fact, you can make more powerful statements. Remember, the sampling distribution of the statistic that we're looking at here is standard normal to an error that's of order n to the minus 1/2. So we go from an error of n to the minus 1/2, first order error, to third order error by this bootstrap calculation. We've reduced the magnitude of the error by a factor n to the minus 1 by doing the simulation, the bootstrap calculation. And that reduction from n to the minus 1/2 to n to the minus 3/2 is something that's true quite generally for any sensible, asymptotically standard normal statistic that you might want to throw at me, not just for the signed root likelihood ratio statistic. So it's quite a powerful result. By contrast, other kinds of simulation scheme, other kinds of bootstrap schemes, in particular, you know, the most obvious bootstrap scheme, the one which just replaces the parameter, does the fitting by replacing the parameter in the model by the global maximum likelihood estimator. Such a scheme has an effect, but in fact, typically, it just reduces the error by an order of magnitude n to the minus 1/2. So for example, if we use the sort of conventional bootstrap approach to the sampling distribution of the signed root statistic, we reduce the error not to third order, but only to second order by that kind of, you know, replacing the parameter by the global maximum likelihood estimator calculation. That's sweeping a few things under the carpet. In particular, if we're interested in inference on a vector interest parameter based on the likelihood ratio statistic, it's not actually quite clear that different bootstrap schemes are preferable to others. Both the constrained bootstrap procedure, as I've described it, and the more conventional bootstrap scheme based on the global maximum likelihood estimator, those will both reduce the error to order n to the minus 2. It's not quite clear from current state of knowledge, as they say, which is going to be preferable in that context, right? And I don't think I've got an example here, but you can look at cases where there's an obvious difference between the two schemes, but it's quite insignificant compared to what you typically get from competing kinds of inference procedure. Okay? Right, here's where we contrive things to give a couple of really toy examples, right? But contriving them so that we can actually see quite clearly just how spectacularly good some of these simple simulation schemes happen to be. Okay, so remember we're looking at things here. Still, I'm not wheeling in these finer points of inferential theory, conditionality principles and stuff. We're just still judging things from a repeated sampling perspective. But I've got two examples. In the first one, the parameter of interest has dimension p equal to 1, but the nuisance parameter has dimension 20. It's some kind of variation of the Behrens-Fisher type of problem. So roughly the setup is that we've got ng groups of observations, and within the ith group we've got ni observations, and the common distribution within that group is that we've got normal distributions with common mean mu and variances that depend on which group, right, you've got, right? So that's the model. The inference parameter is the scalar common mean mu, and the nuisance parameter consists of the collection of variances, okay? And just to sort of pin things down and show a table of numbers, I like tables of numbers, let's suppose this is why you've got a 20-dimensional nuisance parameter. You've got 20 groups of observations, but they're all the same size. So within the ith group, you've got n observations, but we'll vary n, the number of observations. And then just to be specific in the simulation, set the ith variance, sigma I squared, to be equal to I. So you've got variances 1, 2, 3, 4, and so on in the 20 groups. And the table of numbers that I'm going to show compare coverages of one-sided, we've got a scalar interest parameter, so we're going to do one-sided inference, coverages of one-sided, in fact, upper confidence limits for the true mu, which in the simulation was set to be equal to 0, comparing the coverages that we get by the schemes on the one hand, which are based on standard normal approximation to the distribution of the unadjusted signed root statistic, R. On the other hand, standard normal approximation to the sampling distribution of Barndorf-Nielsen's R star, and on the third hand, if such a thing's possible, by the bootstrap scheme, where we construct an estimate of the sampling distribution of the statistic by the constrained bootstrap scheme. For what it's worth, the figure has been based on the drawing of 10,000 bootstrap samples for each of 50,000 Monte Carlo replications. And there's the kind of coverages that we get. We've got the nominal coverages of the confidence limits along there, the coverages that you get by the three schemes, normal approximation to the sampling distribution of R, normal approximation to the sampling distribution of R star, and the bootstrap scheme along there. And n's going down, and even when n is ridiculously small and equal to 3, the bootstrap figures are almost smack on the nominal desired coverages, where for at least for very small values of n, you can see that the coverage figures that you get by the more analytically sophisticated procedure based on R star are still noticeably off the nominal desired coverages. So that's just one example of very many that show spectacularly good performance from a repeated sampling perspective of this. You know, it's the first thing you would think of doing, right, in such a parametric problem, at least where the interest parameter is of dimension 1. Okay. Second example, again, still thinking of things from a repeated sampling perspective. We've got an interest parameter that's of dimension 2, and for some reason, which escapes me, I've chosen just here, I'm not cheating, honest, the nuisance parameter in the parametric model that we're working with here is now of dimension 10 rather than the 20 that we had in the previous example. This is difficult to... Basically, again, we've got the same setup of ng groups of observations with ni pairs of observations in the ith group. The pair of observations in the I group being independent normals with means mu1 and mu2 respectively, and common variance sigma I squared in the ith group. Okay, with the interest parameter being the two-dimensional thing consisting of the mu1 and the mu2, and the variances once again constituting the nuisance parameter. Okay? Same kind of thing. I've taken, because q is equal to 10, take the number of groups 10, but this otherwise the same kind of thing as we had in the previous example. Set the true mu's to be 1 and 2 respectively, and compare coverages now of confidence regions for that two-dimensional thing. Confidence regions that you get either by doing the asymptotic, so now it's chi-squared 2, approximation to the sampling distribution of the likelihood ratio statistic W, and by the simulation scheme, which involves bootstrap estimation along the way of fitting the model as I described, and constructing based on 10,000, the drawing of 10,000 samples using the bootstrap scheme to estimate the sampling distribution of the likelihood ratio statistic. Coverage figures again based on 50,000 Monte Carlo replications. And there's the kind of thing that you get. Now, you've got, you can see that, again, for very small values of n, the coverages that you get from the bootstrap scheme, even though there's a 10-dimensional nuisance parameter kicking around here, are basically spot on, whereas the asymptotic chi-squared approximation is quite poor. Maybe this would be an appropriate point to say, if you, instead of using the bootstrap scheme as I've described, actually devote your simulation effort to estimation of that Bartlett correction factor and based your inference on the asymptotic chi-squared approximation to the empirically Bartlett corrected form of the likelihood ratio statistic, the figures actually turn out to be completely indistinguishable to the bootstrap figures, which is, of course, a little bit worrying from the point of view of the bootstrap calculation, in that a somewhat simpler use of simulation achieves the same repeated sampling effect as the building up the sampling distribution in a larger bootstrap calculation. Okay, but that's all then from a repeated, everything being judged from a repeated sampling perspective. Key, remember, to the, as a driving force behind the development of statistical theory is being, but we have procedures based on R star and stuff that respect things like conditionality principles that we consider to be crucial in statistical theory. And I'd just like to sketch with one very trivial example the properties of these simulation or bootstrap schemes, at least for the case where you've got, this is where we talk about one-dimensional interest parameters in a workshop on multi-dimensional data, but never mind. Properties of this bootstrap scheme when judged against these sort of more subtle aspects of statistical theory. In the first of the two contexts that I flagged, the full multi-parameter exponential family context, it turns out that this bootstrap scheme that I described, so that's the bootstrap scheme, remember, which is just based on plug in the constrained maximum likelihood estimator for your nuisance parameter into the model, and then just simulate away, right, in a completely unconditional way, the sampling distribution of your sine square root likelihood ratio statistic. That's the inference that's relevant to the case where P is equal to 1. It turns out that that scheme actually yields us, even though there's no conditioning going on in its implementation, with an inference that nevertheless agrees with the appropriate inference, okay, my ideal bootstrap inference in this setting, the exact conditional inference, so an error that's still of third order in the sample size. So that's the same order of magnitude of error, even though it's being judged against an inference which is a conditional inference. And so from a conditional viewpoint, we get the same conditional accuracy by the unconditional simulation approach as we do from the analytically more sophisticated Barndorf-Nielsen R-star type of inference. In that same context of multi-parameter exponential families, it also turns out that this simple simulation scheme based on replacing the nuisance parameters by their constrained maximum likelihood estimators actually reproduces what you would presumably judge to be the appropriate objective Bayesian inference in this context. The appropriate objective Bayes inference now, presumably because the appropriate frequentist inference is a conditional one, the appropriate, what I would mean by an appropriate objective Bayesian inference being one which corresponds to conditional second order probability matching or something of that nature. It turns out that in this multi-parameter exponential family context, the Bootstrap scheme matches that objective Bayesian inference again to this same order n to the minus 3/2. In many circumstances, in all the kind of, it's actually the condition under which this holds is actually a condition on the model and not on, you know, anything more sophisticated. So it means that we actually, by just using this simulation scheme, we not only get great repeated sampling behavior of the inference, but we replicate exact conditional inference in this setting and objective Bayes inference in this setting to extraordinarily high degrees of accuracy. I don't have any numbers to show on this particular point, but I'll show you a little example to close on the first of these. Okay. In ancillary statistic models, so that was the second context where I said inferential subtlety is perhaps required, the story is, at least on the face of it, not so great, in that the simulation scheme, the Bootstrap scheme with the appropriate handling of the nuisance parameter, yields us an inference which agrees with the appropriate conditional inference, though the inference based on conditioning on the ancillary statistic, only to second order, n to the minus 1 in the sample size n. And that's to be compared with the property that I flagged earlier of inference schemes based on things like R star, which are specifically designed to give third order conditional accuracy. So on the face of it, that's not so good news for the simulation scheme. But a question that I would like to flag is whether in fact it's sensible in these kinds of setup to actually demand third order conditional accuracy, right? I mean, it's well known that in these ancillary statistic models, typically the ancillary statistic is not unique, right? And if you know, you have one ancillary statistic that you want to condition on, I've got another, then the two conditional distributions that we will separately use for our inference, they're actually going to differ typically at that order n to the minus 1. So having something that gives third order conditional accuracy for some ancillary statistic isn't actually necessarily the most relevant thing. Okay, so there's a really provocative remark that the whole machinery, the R star machinery of parametric inference over conditions in some sense. Okay. Okay, so let me, before just making some very brief concluding remarks, show you the promised example where P, the dimension of my parameter, is 1, and the data sample size n is equal to 2. Okay. The example concerns inference in a gamma distribution. So the model that we're assuming here is one in which the data random variables y1 up to yn are IID gamma with mean mu and shape parameter nu. So that means the common density is of the form given there. The sufficient statistic S in such a model consists of, it's a two-dimensional thing consisting of the average of the sample mean of the y's and the average of the logs of the y's. And sort of framing this in terms of a full multi-parameter exponential family model and thinking about it carefully, you see that in this particular kind of model, the appropriate inference on the mean parameter mu in the gamma distribution, if that's the parameter of interest, is actually, should be a conditional inference. It's one that's, however, horrendous, and it's actually only tractable. You can actually only work out, you can actually only do the exact conditional inference on the mean of a gamma distribution, right, if the sample size n is 2 or 3. Beyond that, one has to resort to some kind of approximation. And what I want to show is that you need to do no further than just doing a simple simulation to effect automatically or to some very satisfactory level of approximation that otherwise intractable exact conditional inference. Okay? So what I want to do is to show a picture in which we compare something I didn't stress before, is that the theory appropriate to multi-parameter exponential family setups actually allows us to assert that not only do we get third order accuracy in approximation of conditional inferences in that setting, you actually get relative, you get a third order relative error of that third order. Okay, so I'm going to show a picture which compares the absolute relative errors of p-values obtained by the procedure which makes standard normal approximation to the sampling distribution of R star, and also the procedure which uses the Bootstrap calculation, which again, I stress, is completely unconditional in the way that we implement it. The p-values obtained by that Bootstrap procedure with the exact conditional p-values, which, because I'm going to look at the data setup in which n is equal to 2, we can actually work out. For what it's worth, the value of the sufficient statistic for the data sample that's analyzed is as shown there. So there's a prize at the end of the workshop to the person who can tell me what this sample of size. It's the first two observations of a famous data set. What is the data set is the challenge for you, right? So we've got a data sample of size 2 with that value of the sufficient statistic. And what I'm going to do is test the null hypothesis that mu is equal to mu naught against the appropriate one-sided alternatives, depending on whether, you know, mu naught is big or small. The appropriate inference is, you know, you're testing against mu is bigger than mu naught, or you're testing against mu is less than mu naught. Okay, so we're going to do one-sided inference against the appropriate one side for a range of different specified values of mu naught. And going in for overkill in the figure, basing the Bootstrap calculation on the drawing of 5 million Bootstrap samples. Okay, and there's the figure, right? What it's showing then on the y-axis is actually the absolute relative error of the approximations for the different null hypothesis values mu naught along the x-axis. Okay, and the red things are the absolute relative errors that you get by making normal approximation to the sampling distribution of R star, and the blue things are what you get by the Bootstrap calculation. Now, for what it's worth, this vertical line in the diagram, that actually corresponds to a sort of left-hand conditional, exact conditional p-value of 1%. And what you can see, therefore, is that the Bootstrap procedure is actually giving us a smaller absolute relative error than the analytic method, at least out until very, very small exact conditional p-values. And honest, again, this is not a deliberately chosen example that flatters the Bootstrap procedure. This is quite typical of what we see over a range of examples, including examples that involve data sets of more realistic size than the n is equal to 2 that we've got here. Because we've got a data sample n, a data sample of size n is equal to 2 here. In fact, if you ask where is the vertical line on the other side, it's way out, about Stories Way or something, right? In that you only get a sort of right-handed conditional p-value of 1% for some ginormous null hypothesis value of mu naught. But the picture, had I chosen to continue here, is, as it seems here, that in fact you get extraordinarily small relative errors from the Bootstrap calculation, even to quite small p-values over at that other end as well. Okay, I guess I'm sort of out of time, so let me just close with some concluding thoughts and flag some further ideas that I haven't touched upon already that I deem are supposed to be worthy of investigation. Well, firstly, of course, is the idea that the bulk of the theory that we have in place of the behavior of these simple simulation-based methods of inference is worked out for the case where p is equal to 2. Theories for p bigger than, for p is equal to 1, theories for p bigger than 1 are much less developed and are surely worthy of investigation. In particular, discriminating how do you do the simulation, how do you handle the nuisance parameter in that setup is not clear. And then also a related issue is what I termed, I think before, the best use of the simulation. Is it best just to use a simulation to, say, approximate a Bartlett correction factor, or should you use the simulation to replace completely the asymptotic chi-squared type of distribution? Of course, everything that we've talked about or done so far relates to the case where you've got fixed dimension d of the parameter in the model, and we're allowing the sample size n to go to infinity. What happens, can we let the dimension of the parameter in the model increase to infinity with n, and if so, what kind of rate? There's a certain amount of work on that kind of issue being done in the non-parametric inference, for example, inference procedures based on non-parametric likelihood rather than a kind of parametric likelihood basis here, but that's something that's presumably worthy of looking. I guess before somebody in the audience attacks me and say, what's the relevance of all this inferential subtlety, I will raise the question myself. Are issues like conditioning on ancillary statistics 20th century ideas? Right? I mean, we're familiar with the idea that, you know, it's said that as the sample size n gets to be anything sensible like 10 or 20, the effect of doing the conditioning is just going to sort of diminish. Should we actually be, when we come to do inference in high-dimensional data problems, be bothered with these kinds of issue or not? Okay, right, discuss. Obviously, there are questions to do with model misspecification and robustness ideas. I already said that most of what I said holds for general asymptotically standard normal types of statistic, but there are robust forms of likelihood ratio and sine square root likelihood ratio statistics that we can use. Those results are going to, that I've given, you know, we could use our procedures with those robust forms of statistic, but then of course we're going to be doing the simulation from the wrong distribution, right? And what goes on in those kind of circumstances. And then I think, I mean, it's already cropped up in some of the talks so far. It's clear that sort of central to much of what's going to be discussed in this workshop and in the whole program is going to be the sort of centrality of the multivariate normal distribution and multivariate normal assumptions, okay? And then, of course, you're also going to accuse me of having played around here with very toy, perhaps uninteresting inference problems of hypothesis testing and confidence set constructions. And clearly, there's much to be done on extending some of these ideas and the analysis of these parametric simulation procedures as the basis for inference to perhaps more relevant kinds of inference problems, in particular things like multiple testing situations, model selection context, and so on. Okay. Right, thank you.
Is there a question? Comment?
When applying the bootstrap in complicated problems where iteration is needed to get the estimates, and needing 10,000 bootstrap simulations to look at p-values, things like that, what do you do about the iterations that don't occur? So your code is reliable on the full data set, there's no problem there, but in some fraction of the bootstrap samples, code does not convert.
I think that's a very good question. Yeah. I mean, I tend to take the view that issues to do with sort of computational efficiency are of interest, right? You know, by tomorrow we'll be able to do a much bigger thing. But that is a question that can arise. In the kinds of noddy toy examples, I suppose it's not something that arises, and then just chucking away some very, very small proportion, right, of samples, or relying on possibly bogus estimates that have come out in those cases seems to do very little damage. But I suppose that perhaps would be a very useful question to add to the list here. As we go to more complicated problems, does that kind of thing become more of an issue than not? Yeah. I suppose you know, if we're doing the implementation in the same way, you keep checks on these things. You know, check that the thing doesn't. You know, the iterations do converge, and there must be some sort of threshold beyond which you wouldn't rely on the calculation at all. But if it's some very small proportion of bootstrap samples that yield some problem, then it might not be too much of a worry to us.
So the connection with this and high dimensional stuff, as you say, isn't clear. In fact, Larry Wasserman and I wrote a paper where we said that doing high dimensional inference means or you should immediately give up the conditionality principle
Right.
and the likelihood principle. You can't do it. And in fact, I think the earlier talks, you can even see that in the earlier talks from today. So our point was there are problems. Let's say you're trying to estimate a coefficient in a regression model with many regressors, like earlier today, but I tell you the distribution of, let's call the regression coefficient I'm interested in, it's regressor x, and the other one's v. I tell you the law of x given v, which is complete. That's the distribution of an ancillary statistic, because you usually condition on the regressors. If I tell you that, you can get much better rates of convergence in big models and so forth by using the information on the ancillary statistic. That indeed, if you condition and try to be conditional, that information is not useful, you can't do well at all. That's our point. The connection, I think, to the stuff earlier today is all these, if you think of that one variable or a few of them as the active variables, the ones that beta is not 0, and then you think of all the other variables in the models, in these L1s, in the sparsity situations where the true parameters are 0, these, I forget what they're called, uniform uncertainty principles, are really assumptions about the distribution of x. They're telling you that all these guys, where the betas are 0, don't predict the x's well in the population for these guys. And that's the essential information on an ancillary statistic that's driving these things. And so I think that, you know, in real high-dimensional problems, I don't know what it means. This leads you in the wrong direction. The likelihood versus good decision theoretic performance are really different if you have make any kind of assumptions about the marginal distribution of ancillaries often, I think.
Well, thank you. That's for that comment.
Okay, very nice. I suggest we have a very short break, 3 minutes, so that Tracy can bring in the gong for the poster session. And then for the moment, let's thank the speaker for his talk.